Once again, I welcome you all in the next session of Mr. Pankaj Podar, Principal Scientist, Physical and Material Chemistry Division, CSIR, National Chemical Laboratory, NCL, Pune. His current research interest includes magnetic ferroelectric materials, materials for thermostics, metallic nanoparticles and quantum clusters, semiconductors including graphitic carbon-based materials, phosphor nanomaterials, biophysics. Specialty with various experimental methods such as advanced microscopic methods, which includes piezo response force microscopy, force spectroscopy, electron force microscopy, electron microscopy. Optical methods, which includes spectroscopic ellipsometry, Raman spectroscopy. Low temperature and high magnetic field setup includes vibrating sample magnetometry, squid magnetometry, AC suspectometry. Impedance spectroscopy down to 2K, magnetoimpedance, magnetoresistance, and Hall effect. Thermal method includes specific heat capacity, thermoelectric figure of merit, thermal conductivity, magneto-heat capacity. Self-assembly includes Langmuir-Blodgett method. Glimpse of some awards and achievements during his tenure. Awarded as the Fellow of Electron Microscopy Society of India in the year 2017. MRSI Medal for the year 2014 instituted by the Material Society of India. Elected as the Fellow of Maharashtra Academy of Sciences in Physical Sciences in the year 2013. Highlighted by the American Chemical Society among authors of high quality research in ACS journals in India 2012. Scientist of the Year Award in 2010 at CSIR National Chemical Laboratory instituted by NCL Research Foundation R.A. Mashelkar Endowment Fund. Discussion leader of a session on spin polarized materials at 2010 Gordon Conference on Magnetic Nanostructure held at USA in August 2010. Young Scientist Award in Physical Sciences for the year 2008 instituted by the Council of Scientific and Industrial Research CSIR India. Received Junior Research Fellowship from 1995 to 97 and Senior Research Fellowship during 1997 to 2000 from Jawaharlal Nehru University, New Delhi through its entrance examination. Under the guidance of Mr. Pankaj Podar, 11 PhD students graduated from his group in diverse fields such as biotechnology, in chemistry, in chemical sciences, in physical sciences, and in biological sciences. Currently, 4 PhD fellows are working in his group with the diverse fields. 3 postdoctoral fellows currently working in his group under the fellowship offered by DST India. Mr. Podar has 3 patents granted and more than 50 quality research papers has been published in reputed national and international journals. Thank you.
Hello. In this series, I'm going to discuss some common mistakes we do generally in measurements and data analysis and its reporting. And this series will connect you directly to the different measurements you do in the lab, whether it is some spectroscopy measurement or it is microscopy or chromatography, anything, even simple measurements using weighing balance. What is the reason that this topic is so important? The problem we see in our country, starting from academic lab to industries, is that we have less training. I mean, we don't have world-class training. We don't follow world-class protocol in taking the measurements, calibrating the instruments, and following the global standards when it comes to the units and measurements, error analysis, different kinds of errors, and also curve fitting. So when we try to compete with other industries abroad, then this problem becomes uh, uh, significant because our products get rejected, whether it is a pharmaceutical product or we face problems in vaccines, and we also face problem in our ventilators. So the problems are manifold. You can see these problems uh, in day-to-day life when you buy, for example, mobile charger from market, and when you buy sockets uh, and you try to fit two things together, you will find that the pin size sometimes is mismatching the distance between two pins or these three pins. It's very different. The quality is very different. And I mean, there's no, there are standards, but hardly any manufacturer um, follow those standards actually. And at the consumer level, we face a lot of problems. Batch to batch, the drugs, the pharmaceutical drugs, they are not consistent, and that leads to a lot of rejection by US FDA. So this problem crops up in many areas. For example, the pressure regulators in in gas cylinders, or whether it is simple thing like when you take your car out and when you fill air, and you can see that when you fill the tires at different um, places, you'll find that there is a big variation in the pressure gauges actually. There's a big variation from one petrol pump to another petrol pump, and there are many times leads to accidents because there are occasions when because meter is not calibrated, so it leads to tire burst and a lot of problems. So most of there are a lot of uh, in healthcare or anywhere, most of the accidents which takes place is because of, believe me, 99% of the accidents can be avoided when we do the measurements and analysis very carefully. Last example is the pollution actually. We measure pollution level through different instruments which are installed, but they are never calibrated. We just get some funny reading. So I'm going to discuss, of course, this topic is endless and it is very serious topic. It is affecting us. We can sell these products in local market, but we can't compete with countries like China. So this topic is touches basically chemistry, biology, physics, engineering, all aspects of sciences. So definitely it is difficult to cover it in a short duration, but I'll give you a flavor and then you can do some reading. So there is an organization ISO which provides a regulation, and there are other organizations also. We need to do some introspection and we'll see that where our country stands actually. First thing, when we go and design any experiment in a chemistry lab, we have to ask ourselves that why do we go for a particular experiment, a specific experiment? What are we trying to, what information we are trying to obtain, whether that instrument is able to give us that specific data, or it just to add one figure or two figures in the manuscript so that it will get accepted. Another thing, whether we hardly bother whether that instrument is calibrated, it is accurate, it is reproducible, it is traceable, and what are the different sources of errors. We hardly bother actually. We just get the data and we believe, we trust that intensity what we are getting from particular spectrometer should be what it is showing, the wavelength should be fine, the data points should be fine, and data representation also has serious problems. So I'll discuss that in the second part. So measure, if you look at any measurement, whether it is whether you do any spectroscopy measurement or X-ray diffraction or anything, we are actually measuring some fundamental values. I'll come to that. So there are there are SI units and there are derived SI, there are derived units from those 7 base units. For example, time, you can go from femtosecond scale to uh, millions of light years. So, uh, and how do you measure it? Well, so the different yardstick will apply when you try to measure in femtosecond region, and then different ways of error analysis will apply when you measure the time in hours or days or years. Similarly, in energy scale, you represent the energy sometimes by wavelength or electron volt or centimeter inverse, hertz, joule. What are the ways that are suitable to you? We do that. Similarly, most of these values comes in the form of some voltage. All the spectroscopy measurement, we actually get voltage that we convert into a useful signal. And dimension also we measure uh, starting from sub-angstrom light years. And when we go to sub-angstrom level or nanometer level, uh, how do we know that our microscope is giving us the value which is it should be, is whether it is calibrated? So those things are very serious things. For example, if you want to take approval from um, some accredited lab, then there are serious problems. Just think about going to a pathology lab and doing your sugar analysis or lipid profile or your thyroid test. Those values are so like nanogram per microliter or something like that, or vitamin D3 or B12. So just imagine from laboratory to laboratory, things are different because these are not machines are not calibrated. They are not calibrated from it. So what is that calibration? How does it come, and how we can um, bring it to our laboratory practices? Why it is relevant? Because if you want to sell some chemical which you have made, so now world is like a big market. So China has already learned these lessons and they are far ahead in this domain than us, and we are really lacking here. So we need to really educate students. So let us see first. The basic thing is that let's understand what are the new international systems of units. In our textbooks, we were introduced long back the older way of international units, but now things have changed. So the rule is that do not use random units and symbols. And I'm sure many of you are using random units and symbols, and I'll give you so many examples. Uh, Even it goes into the uh, scientific journals, and many times wrong things, wrong symbols or units have become uh, common. I mean, it is accepted that it is fine. I mean, for example, AMP for MPA. Second, we'll discuss about that. So we cannot invent new units or symbols. We cannot do that. We cannot do that. Okay, unless you're publishing your data into scientific journals. So we have to follow NIST guidelines, right? Yeah. So I'll just introduce you with these units. You can read more about it, and there is significant change here. So there are 7 base units, and you can see that for example, for mass, kilogram, and distance, and the time, and you can see the current, and the Kelvin, and then the mole, and then this is for the luminescence, pendants. So, so there is a significant change in last few years, and that has simplified the way we used to uh, trace these standards. For example, uh, you are weighing some chemicals in your laboratory using microbalance, and the company will provide you some internal calibration or some external calibration which you routinely um, calibrate. But how do we know that those uh, you know, calibration standards are traceable to the original ISO standards? Earlier, this was a big problem that there will be some prototype which will be kept in a specialized lab somewhere in Europe, and then you need to buy a copies. Different countries will keep copy of that standard, whether it is meter standard or it is mass standard or time for that matter. And then you need to periodically, that country needs to um, keep on sent that, it has to be sent back, it needs to be certified periodically, and then you in your country, that organization which is given the task for that, for example, BIS in India, NPL, they have to uh, distribute those standards to different Indian industries. So that was a very expensive affair, very cumbersome, because those standards were also, original standards were also prone for fluctuation. It was not like they did not change over time, because with time everything changes. So there was a need to make those standards independent of uh, physical entity. Like, it should not become hostage of one lab. So for example, you can make your own standards in your own lab. So how do we do that? Well, I'll give you some examples. Of course, you can read. One finest example is for the mass, kilogram. Kilogram earlier used to be some prototype, some platinum, or some cylinder which will be kept in a vacuum chamber or something, and then you need to make a replica of that. And it turns out that that original prototype will also add few atoms or remove few atoms. So it was not like something which was, so was that itself was not reliable actually. Okay, somebody thought of making 1 kilogram as particular. Uh, these are all man-made. So right. But Planck constant is something which is absolute. You go to any corner of the world, you will have the same Planck constant. So once you decide this constant, then you can link up this mass unit to the to this Planck constant. Then life becomes easy. So then you are not. So for example, so these new unit of kilogram is defined as Planck constant. Of course, it is interdependent. These units are actually interdependent, right? Yeah. So uh, another example is ampere. Earlier, it was very cumbersome that you have to maintain two straight parallel conductors and of infinite length and 1 meter apart in vacuum, and they should apply some force, particular amount of force. Then you have to measure this force to that accuracy. Then only you can say that there is a certain amount of current. In all your chemistry analytical equipments, you have to have certain current flowing, and then only you get some value. Finally, all the signals are actually current and voltages. So it touches everybody's life actually, whether you're driving car or anything, or your laptops or computers, mobile phone. Uh, so now it is very simple because it is linked to the elementary charge of electron, right? And that we know, and from that we can derive the current actually. So no longer we need to do this kind of imaginary impossible experiment like measuring the force into infinite parallel, infinite length, and very thin current carrying wire, which is very imaginary situation. So similarly for the mole, now the mole is earlier mole was like you have to take pure, highly pure carbon 12 and 0.012 kilogram, and okay, and number of atoms in that. It's no longer that. So you just look at the Avogadro number and then you have the mole. Similarly, Kelvin was connected to the triple point of water, which was again very difficult. What kind of water, what purity of water? Water is not the same from point to point. I mean, unless you really take highly pure H2O. But proving that it is highly pure, just all the molecules in certain volume are only H2O. That is, again, you can think about it. How will you first prove that? Okay, that itself requires a lot of effort. So then triple point of that, and then fraction 1/273. So you can see the complexities. Now it is very simple. It is connected to the Boltzmann constant. Similarly, meter. Earlier it was, it started from a length, started from the foot, length of the, foot of an emperor. Then it got refined, and now it is all gone. It is linked to the speed of light. So simple. It sounds simple, but maintaining those standards in the lab, uh, you have to make a full-fledged laboratory actually now. Earlier, the lab, it was not, you need a setup, experimental setup to generate those standards. Earlier, you can just buy something, you can buy, for example, clock to keep the second. For example, now clock is basically a cesium 133, some particular frequency, some particular emission. You can link it up. It's so simple actually. Similarly with the candela, you can see on all the bulbs there is a value, and right. And so earlier it was like candela means basically it was coming from some candle uh, originally, but now it is much easier actually. Now these are 7 fundamental units, but we normally work with the units and symbols beyond that. Those are actually derived from that. Originally, these are the fundamental ones, and there are the derived ones. I'll talk about some examples which are derived from these units. So once you have understood those 7 units, how we once you have standards in your own country, and for those 7 base units, then you can have some confidence in, for example, measuring area, which is actually derived unit. Volume is a derived unit. It is derived from meter. That is fundamental unit actually. Speed velocity, again meter per second. It's a derived unit. Acceleration, wave number is again meter per second. It's a derived unit. Density, anything, magnetic field strength, luminescence, mass fraction, plane angle, solid angle, all those things are. So radian is derived unit. It's not at all, degree, for example, is not at all a fundamental unit. You have seen that it's not at all a, okay, we use it, but for example, hertz is a derived unit. Centimeter, second inverse is basically fundamental unit, base unit, or I call it. So we don't sometimes realize that it is not. For example, volt is not a base unit, not at all. You need to write volt in terms of base unit, then it will become meter square, kilogram, second power -3, and then ampere inverse. So you can see the difference because you have standards for these units, not for. You don't have a standard for centigrade. You don't have a standard for Tesla. You don't have a standard for Farad, capacitance. I mean, those are derived from it. So, um, for example, laboratories do not keep the standards. And there are need and we don't change a lot. See, years, more than decades, we don't really change. So we mess up a lot between names, symbols, and prefix actually. Okay. For example, second is not allowed. Second is not at all abbreviation of CC is not allowed actually. Centimeter cube is allowed. CC, we use CC, but it is not. MPS is not at all allowed. It's not meter per second. It's meter. So you can see that for second it should be S. Even for seconds it should be S. So there is no singular plural when you represent the units. Similarly, you should never write cubic centimeter like CC. You should always write centimeter. You can see that it is too common that wrong things have become common, especially in our country. You can write these things in newspaper, but prefixes. So prefixes are also standardized. You cannot use any random, and so because you need prefixes also. Plural unit symbols are unaltered uh, in the plural, similar to plural. For example, centimeter, 75 centimeters is not written. It should be cm, centimeter. Punctuation, we do a lot of mistakes. For example, you can see that here in units we write for amperes, we write amps, seconds. We see a lot of problems. Punctuations also, unit symbols are not followed by a period unless that's the end of sentence. For example, you can see that here there is a period, but it's the end of the sentence. Many times, many people write period, especially chemistry students, but it is not accepted. You should never do that. It's not correct. Next thing is the rule about multiplication and division of the units. When you represent the multiplication, either you just leave a space or half high dot. When I say half high dot, you can see it here. Half high dot is generally used as nothing else. Nothing else is you can't use um, a cross or something. You don't use that either space or half high dot. You can't invent your own method here. It's not accepted because that's not standard. Globally, we have to follow one rule. It should not happen that Pune people follow something else and then Satara people follow something else, or Surat people are following something else. Actually, it is not like your way of making roti or dal or something like that. It's not like that. There is no scope of any modification here. When you represent the division of units, you normally represent it by a slash, backslash, or horizontal line, or negative exponent is also used. So now here you have some examples. For example, speed of sound, if you want to represent, for example, 344, and that is meters per second. So how do you write meters? Will be m, not ms, and then dot for the multiplication, and then second per second you can write second inverse, or you can write backslash without any problem. Decay rate of cesium 113 is 21 milliseconds. So you can see that it is not the it is a prefix. Milli is the unit prefix. Please note the difference. It is not the unit, it's a prefix, milli. So here you write m, and then no, you don't write here any half I dot. There is no gap here. You can see that there is no gap here. There is no gap here. Please note that many people, many times they will just put some space here, or because it looks good, and they may, and in another slide they may, that gap may disappear. And another thing, you can see that the unit and its symbol, there has the value and the value of the unit and its quantity, and then its unit symbol, there should be a space, only one space. Sometimes people put this side by side without any space, or sometimes they just follow. This is a common problem in India, that there is no consistency even in the mistakes. I mean, everywhere there will be some variation actually. And similarly, you can see some of the other examples. So yeah, typeface. Here, most people fail here. I mean, I have seen even my own writing that I have to be very mindful in following the typeface. Typeface, we are completely ignorant actually as Indian researchers. Normally, the typeface correction is, we leave it to the editorial office, and they have hard time when they get manuscripts from Indian authors. They spend a lot of time. Thanks to them. Variable and quantity symbols are italic type. Please note that. Variable and, for example, time t is italic, okay, but the unit is not italic. Unit symbols are Roman type. Numbers should be written generally in the Roman type, and these rules apply irrespective of the typeface used in the surrounding text. For example, she explained, comma, and then you have these inverted commas, that dog weighs 10 space kg. You can see that there's a space here, and this is an italics, and this is Roman type straight. Okay. Now, another example, the time is 3 seconds. Okay. So you can see that time t is a variable parameter, and this is the value, right? So for example, temperature T is equal to 33 Kelvin. So T will be here in italics, and this will be in Roman face. So this is improper. You cannot do that. 10 kg cannot put in the italics. And similarly, here you can see that time t, here this is variable, so it has to be in italics. That shows that it is variable. In fact, it shows that it is not a constant, it is variable. That basically also helpful in differentiating it. It basically, in a way, it make our scientific writing more organized. Okay, that it is not constant, it is variable. So for example, this is improper. Subscript and superscripts are always in italics. Most people don't even bother to make subscripts as subscript. It takes effort, so they just leave it like this. But don't do that. They are italics if they represent variables quantity. They are Roman type if they are descriptive. For example, specific heat is written CP, it's like this. You can see this. Abbreviation. This is a very controversial topic. you will be surprised to know, and most people may not agree with what I am showing, because it has become so common. And so, for example, percentage is unscientific. You cannot, percentage symbol itself is unscientific. It's not proper. It should not be written. Forget about ppm, ppb, and ppt. They are not at all approved by international organization. The reason is that different countries, the million stands for different things, different numbers, different countries. For example, billion, trillion. T does not always stands for trillion. B always does not. So this is actually cultural issue. You might be thinking that M stands for million, B stands for, but it is not like that. That's a major problem. So in pure scientists who are perfectionist purists, they avoid that. For example, you can write microliter per liter rather than writing any of these amount. I mean, there is a way out, right? You can write like that. Okay. For example, 7 picosecond per second. So these are actually pseudo units. Actually, these are ppb, ppm, percentage. These are pseudo units. Percentage of what? The percentage does not itself by itself has no meaning. The percentage of what? So in science, and if you look at the Wikipedia page, it's a long page. I mean, here a lot of discussion is there. So, but I have just taken few things. In science and engineering, part per notation is a set of pseudo units whose it describes smaller values of miscellaneous dimensionless quantities. For example, mole fraction or mass fraction, right? Since these fractions are quantities per quantity measured, so they are dimensionless, obviously, quantity per quantity measurement. They are just numbers with there's normally we represent them as, for example, these are dimensionless because liter by liter, right? So this cancels out and then it becomes dimensionless. This notation is not part of international systems of unit. It's not at all. And because why they had difficulties in accepting it? Because they realized all the countries, when they had together, they realized that the meaning is ambiguous. It's not scientific at all. And there are many problems associated with that. You can uh, even according to IUPAC, this is a continued source of annoyance to unit purists. I mean, people use it, but it's a problem actually. It's a problem area because these are not recognized at all. Similarly, with the percentage is not formally part of SI. Both the PIMP and ISO take position that in mathematical expressions, the internally recognized symbol percentage may be used with the SI to represent the number 0.01 for dimensional S quantities. So these are SI non-compliant, and there is a confusion between long and short scale, because T can be 1,000, T can be trillion. So if you read more about it, you will be thrilled to know that it is. You'll agree with that. That's controversial. T is not always trillion. Actually, T can be 1,000 actually. Unit modifications. Unit symbols are not at all modified. You cannot modify by putting something else. You cannot put variables can be variables. For example, you cannot put subscript or superscript. For example, these are variables. You can change them. This actually it should be in italics here. For example, maximum voltage V max 1,000 voltage, right? So then you can write. You cannot write max V max here actually. So intermixing information with SI units. You cannot write information, for example, H2O per kg, you cannot write. This H2O is an information. It's not like, for example, 20 ml H2O. You cannot write. You have to write water content is 20 ml per kg. 20 ml of water per kg should not be written. When people do that, so it should be avoided. Now we come to a little bit more advanced things. There also we a lot of mistakes, and if you look at your own writing, you will realize that you're always wrong here actually. And it is very, it makes this is a very common problem. And let's dive deeper into that and let's understand what exactly is the problem. For example, look at this 35 to, when we define, for example, range, particle size is from 10 to 20 nanometer. What is 10? 10 has some unit, it's not unitless. We should write 10 nanometer to 20 nanometer. But normally, for example, frequency range is 1 megahertz to, so we should not write, for example, this dash should not be written. It should be 1 megahertz to 10 megahertz, or we can write like this. So for example, we don't have space, so we can write it in bracket 1 to 20 and then megahertz. Similarly, this is a common mistake. In chemistry, we write temperature. That reaction temperature, we vary temperature from 20 degrees centigrade to 30 degrees centigrade. But most of the time we just write 20 to 30 degrees centigrade. Right. Same with the gram. 123 plus minus 2 gram. What was the mass? That was the 123 plus. But what is 123? What is the unit of 123? We have to write it here. What is 123? It cannot be just a floating something. So it is not acceptable. So this is, despite of me telling people at many institutes, most people I can see that by habit pattern, because these wrong things have been hardwired in our brain from childhood. So involuntarily we tend to repeat the mistakes, and more we repeat, more wrong things become permanent, and then we translate, we propagate the wrong things to the next generation also, and this chain never breaks. And in fact, next generation adds their own myths and misinformation when it comes to reporting of the scientific data, and it becomes, or it is becoming a nightmare. It is becoming a mess. And I go back to my original thought. When you address scientific community internationally, when you try to sell your chemical abroad, when you write the specifications, label, put a label on your product, and most of the time those labels are rejected. And I have worked very closely with pharma companies on entire my scientific career, and FDA, US FDA give them hard time, and they are really, when we have no, for example, the purities. Actually, we don't have a purity standard. We don't measure it. Many times we'll get 10 different, all the time different values. What is the reason? Because we don't, our instruments are not calibrated. I'll come to that into the second part of my talk. Um, Unit symbols and names should never be interchanged. They cannot be mixed. For example, you can write kilogram per meter Q, or you can represent this also this way. You can write half I dot and then -3. But you cannot write kilogram here and then meter here, because these are the name of the unit kilogram. However, you can still write, if you have space, you can write kilogram per cubic meter. You cannot just write a symbol and name you cannot mix up. Numerals and unit symbols. For example, here you cannot write 5 kilogram. You have to write numerals actually 5. For example, current was 15 ampere, so this is fine. But you cannot write. You cannot replace A with ampere with. You cannot write this the name of the unit. Ampere is actually the name of the unit. It's not the symbol. But many people write this way, 5 kilogram, they will write this lazily, and assuming that it is all well, and it's unacceptable. Unit spacing, that's where again we see a lot of problems. I mentioned this just now, but we need to leave a space between the numerical value and its symbol. Always, always. इसको चिपका के नहीं रखना है. You should not. Many times we put this, just next to each other without any space. And see, in the same text or presentation by the same author, I find in the next place, I find that it is something else. So there is no, I tell my students that even when we make mistakes, we are not consistent. Maybe we have some wrong notions, but we are not consistent. For example, I have seen that people will, they're not consistent even in their mistakes. So for example, okay, fine, you know that you are taught incorrectly that 25 kg can be put next to each other, but you will find that this is not followed. Sometimes they will write something, and another problem which I find Indian writing is that suppose they have to write a comma here. I'm talking about grammar. They will, after sphere, they will leave space and then they will write comma or full stop. So punctuation, I don't know what is the logic, but before writing any punctuation, for example, here they will leave some space here. I ask them what is the reason that there is a space. It looks good to them. So they said, why like it? I like this way. For example, there is no space if you see this punctuation. Here there is no space. They will leave some space here after used and before comma. So most of the time the logic is that, oh, I like, this looks good actually. That's why I like. And another problem is that they will, most of the time people will make any letter lowercase or uppercase for no reason. For example, suppose here gold comes, you have to write gold. They will write gold ka G as upper in capital. What is the logic? No logic. Because it is important here, so I'm writing like that. So they don't, for example, any other chemical they write. Suppose some chemical appears here. So if they want to highlight something, they will write first letter of this word, which is nonsense, which is not correct. You can see in office poems, they follow this practice for some reason, I don't know. But in scientific writing, we should not do that. We should not do that. And anyway, this is not related to topic of units and measurement, but you can see that angle, yes, you can write here. This is an exception that when you write like degree, you can write some because these are superscript. But here you should not leave space. This is incorrect. And definitely, many times people write this dash. Some reason, I don't know who told them. They just write. There are n number of ways to write. Digit spacing, again, we have no standard in our country. No, absolutely no standard. People write all kinds of things actually. All kinds of ways. Some of them are cultural, historical. When we used to live in village, disconnected from outer world, we could have our own language, our own way of writing maths, fine. But now when we communicate to each other, so we have to standardize everything so everybody across the globe write in the same way. Otherwise, it becomes very confusing. It becomes confusing. So be aware of these things. Again, standard symbols are written the way they are. For example, tangent 10, it is written 10x. R is written for resistance. You cannot write TG, for example, for tangent. You cannot write like that. It's not, you cannot do that. And here, a big problem, weight versus mass. We as a science student confuse uh, between weight and mass. It is fine when you are using communicating with laymen, but people, for example, in thermogravimetric analysis, you will always see almost 99.99% time that we write weight loss. This chemical has, after heating, it has this weight loss. It should be mass, it should not be weight. But we confuse weight and mass. It is a big problem. Last thing, once you have done the measurements, we do a lot of our documentation in India. I have seen consistently that I have seen the difference between Western countries and India. Our documentation is very poor because we were like culture where we used to keep like oral tradition. We were not like written tradition. So we want to keep everything in our memory. And we don't care to know the data file, its format, that we might be needing it after 5 years, 10 years. And we need to keep for example, you are providing some data to industry and they might need the data after a few years, and you should have always keep raw data, don't keep a processed data. For example, dynamic light scattering, people just take a photograph of processed data and they say this is the DLS data. DLS data is not what those peaks actually or those mean values. DLS data is completely different. That is basically that comes from your correlation function. And then the instrument software does the processing and what you get is the process data. For example, roti is not the final data. I mean, this thing, the data actually, the raw form, that's a processed food actually when you, okay. Um, so always keep record of humidity and temperature. Most of the time, I mean, when I did my PhD, I used to always record every day. I used to record what is it, temperature. Whenever I was doing measurements, I would record the humidity and variation, because that matters a lot when you are doing any chemical synthesis. Problem is that when you report in your scientific communication, you write room temperature. This reaction was done at room temperature. Somebody will ask you, what was your room temperature in summer, winter? Oh, no, I don't know. Then you write 25 degree. Who told you that room temperature is always 25 degrees? Did you maintain it? Because in Europe, they keep the lab temperature at 25 degrees. So we assume that it is, so room temperature has no meaning. It's meaningless unless you follow some standards. So it is always practice that you can write room temperature, but you should write the value. The room temperature bracket, this was my room temperature at that time of the year. So that's it for this round. Thank you very much. Hello, this is the second part of my lecture where I'm going to discuss the same topic, how to improve the scientific measurements and its analysis, common mistakes we do, and how do we report the data. So it is difficult to control the uh, all uh, the scope of this lecture series is quite wide, but I'll cover only the important part in the second lecture. So here we start with the familiarization with some definitions, useful measurements and analysis. So first question is that what is the goal of and answer obviously is that you want to report the true value. But here the problem starts that what is the true value of your measurement? Suppose you want to do any measurements, the length measurement of any particle, any nanoparticle, or any volume measurement or viscosity. So how do we know that that value is what we are looking for? What is the error from the true value? So, so is there any answer that how do we know that this is the true weight of true mass of the object, for example, or this is the true dimension of that nanoparticle? Again, we trust on some other instrument, and so it's the answer is very complex. So most of the time we do not know. Most of the time we do not know the true value of that particular measurement, and we can go closer to the true value, much closer to the true value, and uh, that's where the uncertainty comes. The closer we can go to the true value, the better we are certain about that value. And finally, I think all of you know that finally the uncertainty is at the quantum mechanical level is controlled by Heisenberg's uncertainty principle. For example, one can demand that what is going to be the true position of an electron, and which is very difficult to know. The Heisenberg's uncertainty principle. Similarly, when we look at the frequency value in a spectrum, so suppose you reduce the delta E, energy uncertainty, then time uncertainty goes up. So you can see that there is no actually true value, which can every instrument true value comes anyway from an instrument, and every instrument has a fault in it, and which is limited by fundamental physics. So, uh, so those are the limitations when we should keep it in mind. And of course, we are governed by uh, the ISO that I mentioned in the previous lecture, and this both are strongly connected. The previous lecture and this lecture. If you understood the previous lecture, then you will understand that how we can at least do the measurements properly. Yeah. So scientifically accepted true value is that comes from a certified or accepted reference value. It's very difficult to have the reference value of particularly your specimen, your type of experiment, but then you have some traceable reference. For example, for length standard, you can buy a standard for length, and you can calibrate your instrument. Then you can keep on checking the accuracy of the measurement, and precision is very easy to find out, but the problem is with the accuracy, right? Whether it is accurate or not. And so one must rely on, for example, temperature measurement in Kelvin. For example, you want to look at the temperature of liquid nitrogen, around liquid nitrogen. So you use particular temperature sensors, and whether they are reliable, they are certified or not. And so we look at the sources of error. So yeah. So most of the time, what the problem is that India does not have its own industry for references. And so most of the time you will see that we are relying on Western countries for references, and those references come at very high cost. And these references are also, it's not like once you buy, you can start keep on using. You have to keep on validating them. You have to keep on, you have to periodically, they have an expiry date actually. It's not like you can keep the standard. Most of the standards have, varying amount of expiry dates, and that's where the cost goes up. You can, you can have a traceable reference in your own country or your own territory. There are specific labs where you can do all that. But there is a cost involved, and now China is interested in this costly business, which is very has high margins, and China has planned for uh, controlling this aspect. And once the country which controls the references, they pretty much controls the quality of all the products which are sold in the market. So if you don't meet the, for example, Indian industry is manufacturing some product and references are sold by China. So if China does not follow ethics, they can manipulate their own standard, and then you have to follow their standard actually. And many times you can see in pharma industry, FDA is pretty much gives rough time to Indian pharma companies, and whether their protocols are good or bad, you have to follow them, because once they are published, and they mostly favor their own industries of their own country. So there is a big um, uh, interest involved of it's basically nationalism. I would say that's why I was trying to spend more time that this lecture is non-trivial, because it's a big problem in our country that we do not know actually the true value of the measurement. For example, if you buy a gas in your chemistry lab, a vendor can tell you that, okay, this is this purity, that purity, and they can also give you a certificate. But do you trust the purity of the gas? And many times I have noticed that very high purity nitrogen gas, if I'm using in TGA, they're not exactly, they don't meet the purity standards. And but they sell and they make good business. And most of the time, vendors know that we do not have any way of checking their certification, their product, and they take advantage of our weakness. For example, some vendor test sends you sells you a machine, a microscope, and you use the microscope to measure some particle size or some other object, some other for example, uh, diffraction d values or something like that. So you have to trust the vendor. That's it. The vendor knows that it's all, you are dependent on the vendor. You have no homegrown industry. Uh, so I hope you get the message of this serious problem. And it is listed in these concerns are listed in this slide. That's where the problem starts, especially in India, because we were rarely serious about having standards. And look at the size of the industry we have. It's just growing: petroleum industry, pharma industry, and automobile industry. There's so many measurements taking place in these industries, right? Steel industries there and all that stuff. So how do you and everywhere you have uh, hundreds and thousands of sensors, they're taking constantly data. Just imagine one plant actually, how many processes are happening in one plant, and you need to monitor at certain level so many parameters. And so when you finally the product comes out, you have to write something on the label. And for example, this is a protein percentage, fat percentage, and different kinds of fat, different kind of proteins, and further. Just an example, carbohydrate. But when you write some value on the label, and so uh, uh, and you want to export, the country can say that, oh, I don't accept these values. How? What is your reference standard? And so is giving tough time to many industries. And pharma industry is the worst sufferer. I think most of the chemist community, they know about it. For example, we don't have. I am not sure about 2021, but till last year we did not have a certified lab to test our athletes before sending them to Olympic or some other international games, or presence of any doping in their samples. So then India had to send the samples other countries, for example, Russia, and they will charge huge amount of money to do one test actually. So you do your own test, vitamin B12, D3, you can, then that's your own problem. You are not, the other person is not concerned. So, but the moment uh, there is an interest of other country involved, part of the picture becomes highly complex. And so let's discuss about uncertainty and where it comes from. It's a very complex topic, so I'll try to simplify it without going into too much detail. So uncertainty is basically the range of variation in the results when you repeat the measurements, right? And how much it can vary. And obviously you have to take the median, and then you say you just always keep on observing that how much it fluctuates to the sides. So why should physical quantities should vary at all? What is the so that's where we can classify these things. So there are some examples that nowadays actually these uncertainties because instruments are becoming much better actually. So these uncertainties are becoming less problematic. For example, just imagine the analysis of MRI data. Uh, I think all of you are aware of problem with the image analysis. Most of the time, these MRI doctors, experts, they spend a lot of time in analyzing the images. And if you give the MRI image to four different experts, uh, four different experts will have four different opinions. So that's where you can say that there is an human uh, interpretation error. There is an uncertainty. And you can see this uncertainty in our judicial systems also. And there is a very nice book about Daniel Kahneman, Noise. The title of the book is Noise. And I encourage all of you must read this book. So, because many times we have our own uncertainty in our own human interferences quite a lot. So, especially where you do the image analysis. So this machine learning and this neural network and all this these things are making things much easier. And in fact, machines can do measurements much better than doctors can do. Similarly, suppose you have to do manual interpretation of TM analysis, TM images, then it is most likely that humans will do mistakes. But if you let the machine do it, and then put it in the program where there is an artificial intelligence, so the machine keeps on becoming better and better. So there are chances that machine may outperform humans. And one of the perfect example comes from the days where we used to take the readings manually. I remember early days when I started my PhD in 1995. Many times we would take data on piece of paper, drawing the table and then recording the values. Then I automized the entire all the instrument, 4 or 5 instruments. I wrote a lengthy computer program. It was 96, 97, and then I started getting highly. Uh, there was no human error, so I could record more digits, and there was no error. At least in the recording, I could see the online uh, plotting and analysis was easier. So you can see that the variability that data quality became much better when this automation happened. Of course, one has to be very careful with the machines also and the softwares also. That is another topic. That machines and softwares can make ends to elephants. Um, yeah. So I think all of you know what is uh, uh, what is the range of so, so there are two essential components: the numerical value of the parameter which you are measuring, and the degree of uncertainty plus minus whatever value you report. And we already discussed this point that quantum physics places some fundamental limits of the ability to measure things. So we should not forget this. Now, we can broadly classify the sources of uncertainty or error into three categories. Number one, systematic error. Number two, random error. And number three, blunder. So systematic versus random error. Now it's easy to understand. Right? For example, systematic error, you can see that the easiest example is X-ray diffraction. You can see a systematic shift in theta values towards right-hand side or left-hand side. And you know that there is a problem with the goniometer and it has to be fixed. These errors are easy to identify, and you can you can fix, but you can fix only when you know the true value. I mean, in some cases it's easier because, for example, standards you can locally uh, uh, just you can have, for example, some naturally occurring components. I mean, naturally occurring materials. For example, silicon oxide is naturally available. You know that silicon oxide in some particular uh, plane, you know that this is going to be the d value, which is already well known, and it is not going to change. Silicon or silicon oxide. So you put that into the X-ray diffraction, and then you look at the peaks. And if you don't find that peak at the right place, which is already known, and it's not going to change, uh, so then you can fix the systematic error. Similarly, in other spectroscopy measurements also, um, it is easy. So you don't need to have a certified reference. Sometimes references, yeah, you can just get from your own laboratory. You know that, for example, particular dye always shows you emission at particular wavelength. That becomes your standard, so you can check against that. And efforts should be made to take those standards. For example, those are chemically stable. For example, silicon oxide is considered as fairly stable material. So I prefer silicon or silicon oxide. For example, you can crush silicon and powder it, and then you can use it as a sample to fix the systematic error. So So there are various sources. We'll discuss about that. So there is one of them, one of the major source of systematic error is the instrument itself. So instrument do change. For example, atomic force microscope, um, it can show its own aging. Calibration won't last long, so you need to keep on calibrating things. And mechanical parts, they tend to wear out, and there are all kinds of drifts, for example, due to change of the temperature. Noise values can drift. For example, you put uh, another equipment close to your um, main instrument where you want, which you want to look at the, you are looking at the uncertainty. So you will see that whenever there is a change in the building layout or building, some instruments are newly installed. So you will find that there is a change in the readings which you are getting. They are different, much different than the true value which you used to get earlier. So those things have to be carefully seen, and many times we ignore uh, those subtle things. So all instruments are subject to uh, changes. They are not like perfect. So, but most of the time, what happens that we forget that, for example, weighing balances. There are hundreds of weighing balances in it, in a typical university or a national lab, and many times we forget that when was the last time it was calibrated, or so we don't really. I mean, there are sometimes internal calibration standards, but they are also subject to. They are not like perfect. They also need to be checked against the traceable reference. Uh, uh, Life easy if you want to go towards perfection. Uh, it's not that easy, and yeah. Uh, the second part is the operator skills, and that is where a lot of seriousness is there. And the if you give same samples to two different operators, you will realize that you get sometimes different values, because the way the operator, it's like you have your own car, and you're driving. Let the other many people drive it, so their experience will be very different. Actually, car is the same, and probably the road is the same. So we see this problem all the time in scientific measurements, and obviously a lot of training part is involved here. Operators needs to be trained, and SOPs, standing operating procedures, should be well placed so they don't drift from standard procedures. They follow a certain procedure over and over again. Then we know that there is a reproducibility, repeatability. Those things are maintained. And of course, there are international treaties, international laws, which should be applicable to all the labs internationally when it comes to any measurement. For example, XRD measurement, XPS measurement. And those standards are actually coming very fast these days. Very fast. ISO is actually setting out new standards, new guidelines. And it's certifying them. And the problem is that those documents are expensive. They are actually not free. Uh, Industry can afford them, but you need to buy from ISO, and that's the problem. But those standards make life much easier. For example, you want to do the particle size measurement using AFM. There is a ISO guideline for that, and if everybody follows that guidelines, then the uncertainty can be controlled actually. And then uh, suppose you are selling that data to industry, the industry can say that you can tell the industry that, okay, I have followed uh, ISO certified protocol for the particle size measurement using my AFM. So you can certify. You can also certify that that process is well laid out. Then this data will be respected internationally. And similarly with XPS, uh, like for example, binding energy data, or so so there are standards which should be followed, but normally we do not do that. And within a lab also you can see that you have several students, quality of data and their interpretation analysis, everything changes so much. Sampling issue, samples are also it's actually a major problem. So the time um, sampling is a serious problem in the especially in the chemistry lab, and that's why we always say that two reactions cannot be same, and you get sometimes different products. Actually, slight variation um, can make a lot of changes in the nucleation growth. For example, you're growing some material out of solution phase. For example, if you have catalyst lab or anything, so slight variation can do a lot of changes in the catalytic properties. And most of the time, we are wondering that what made this change. If we are careful, for example, suppose we got this conversion ratio 75, next time we got 80, and then we got 65. So obviously, you can get away by reporting that a very broad uh, range. Okay, my conversion efficiency or whatever the catalytic reaction is 65% to 80%. But we now never go into the detail. What is the reason that we are supposed to report such a large variation? Definitely, it is coming from the issues which we are discussing in this presentation. So implications are huge. Indian industry, some industry which is not very careful, for example, may accept your product. Okay, you are reporting the use uncertainty in your catalytic efficiency, but suppose there is a big cost involved by industry. So just even 2-3% change can make a lot of difference to an industry. So it case to case, it really matters a lot. Same thing is with the, I mean, for example, you are selling it to product to the pharma company, and if it is, there are some impurities, and there are toxic impurities. So then you can understand that it will be unacceptable. And many times, most laboratory products do not reach to the market because of we do not care about uh, these uncertainties or measurements. Finally, environmental changes. How many people measure record actually the temperature? I discussed these problems in previous lecture also. And when we say that we are carrying out this temperature at so and so room temperature, but we hardly give a definite value of temperature and humidity. And you know that the product, even if you do in the inert condition, the gas which you used to carry out the inert environment may not be certified. Actually, I have seen a lot of problems with those so-called inert environment, and they are not at all inert. Actually, uh, most of the time we do not know because we don't care to check. Just want to publish some paper, some data is coming, and nobody really checked. Neither authors are checking carefully, not the reviewers, and those a lot of junk get published into the scientific journals. Actually, most of the time, data. I mean, these days, especially, data is rarely reliable. Actually, you can't trust on the. Uh, uh, so, so these are the complex steps of evaluating uncertainty. If somebody would like to go into detail, that you have to make a very complex mathematical model, and this is reserved for mostly for physics communities. I'll skip it. Approximately 12 steps. Random uncertainties are more difficult to manage, and they can just um, can be observational and environmental. Mostly there are human errors involved. And then finally, blunders and or mistakes. And again, those are now less frequent, but you would have seen in RT-PCR reporting, data reporting. So, for example, somebody got RT-PCR, analysis of COVID positive. So many times it was seen that the person who was recording will write it negative. Many times this happened. The actual machine data was different, but on paper it was mentioned as negative in the register. So obviously in most laboratories this process is automatic. So the machine prints the report, and so there is no scope of personal error. But in smaller cities, for example, they write on a piece of paper, so they will, for example, the person is talking on mobile phone, and so these errors, just blunders are so many, and then it becomes an issue of life and death. Trust me on that. Finally, I will touch upon confusion which exists, especially in the student community. We confuse between precision and accuracy, and this confusion can be easily sorted out by this slide. So you can see that on left hand side, you can see this data scattered is highly precise, but not accurate. For example, it should be the true value is somewhere here in the middle of the center of the ring. And then if you see this graph, this data sets, you can see that they're more accurate, closer to the center of the ring, but they're not precise. They're scattered is quite long. So again, in this example, you can see that red is more precise than the blue, and but both are almost equally inaccurate actually. So so these are the important differences here. Finally, this slide is very useful. That I mean, traceability is how do we know that this is accurate? We have discussed it. So there is a hierarchy here. So there are international standards which are maintained by various labs, and then there are national metrology institutes in almost every country. There is one or two certified laboratories, and then for example in India, CSIR NPL is the National Metrology Institute, and then associated with that we have this NABL accredited labs, and then finally it goes to labs or user industry, then manufacturers. You can see that it's a hierarchy, and anywhere something wrong can happen. If one of the laboratory alters, then there will be a problem. So these things I think people know, repeatability and reproducibility, and when we report any data, we should be careful about their reproducibility and repeatability also. For example, by changing the laboratory or making the identical specimens. Many times what happens, some labs, this effort that is ship the sample to various laboratories across country and ask them to measure the specific value using their instrument. And of course the protocol is remain fixed. And finally, the data from, for example, 20 different laboratories across India, it is collected on the similar specimen, and then you can check problem of the uncertainty in the measurements. The resolution is basically, you can see that you can understand that suppose you do the measurement of how close you can measure points actually. That is resolution, and which is sometimes people show resolution much better than the precision, which is misleading, and this problem happened so frequently, especially in the transmission electron microscopy, atomic force microscopy, even in XPS binding energy. So many times it happens. So we have to be very careful. What is the uh, true resolution? And because sometimes digitally we can inflate the fake resolution, but that is not the actual one. Digitization is bringing the problems also. For example, you divide 10 by 3, you will get 3.333. So where do you stop? So there has to be a human intervention there. That what is the cutoff? So finally, I will stop this lecture here, and I hope that I was able to convey my message successfully to all of you. Thank you very much.
Thank you very much, sir. It was very nice and informative session for all. Thank you very much once again.